Hello, I'm Eliska Buys. I'm from Bloemfontein and I am a science teacher at Oranje Meisie School. And we are going to talk about electrical circuits today and the calculation of VIR terminal, V terminal and V lost. So here we go. I have a couple of questions, and as I go along through these questions I will explain some terms and everything to you. The first one we have says that the unit of measurement of the rate of flow of charge in a conductor is. The first thing that you must see is that they ask for the unit of measurement. But before we can know the unit of measurement, we need to know exactly what they're asking for. So what are they asking for? The rate of flow of charge. Now there are two words in here that's very important. And the first one is charge, and the second one is the rate. Now our symbol that we use for charge is Q. And then every time that you see anything that has to do with rate, it means that time is involved. So we need to know how much charge flows per second. So if we put the amount of charge over time, we get that Q over T equals I. And this comes from, if you see the page with all the formulas, you see that they give it in the form Q equals IT. Now if you just change the subject of that formula, you'll see that Q over T equals I. So the rate of the flow of charge is current. But they're not asking for current, they're asking for the unit of measurement. And the unit for measurement of current is amps. So the answer will be C. In the next question that I have for you, and this is a typical question for the end exam, for the matric exams. So if you ever see this one, work through a couple of them. There are a few variations of this one, but this is one of the examples that I brought for you today. It says, in the current represented below, the resistance of the variable resistor is decreased. So they take this resistor and they make the resistance lower. Now, whenever you get a question like this, there are four variables that you must check. The first one, and you must write these steps down as we go along. So I'm going to give you a chance to write them down, but we have to check four variables. And the first one is, you must check what happens to the total resistance in the circuit. The second variable you must check is what happens to the total current in this circuit. The next variable you're going to check is the V lost. What happens to V lost? And then V lost is because of the internal resistance. I think you all know that. You should know that V lost is because of internal resistance. Energy that goes lost because of internal resistance, and that's why the battery gets hot. Okay, and then the fourth one you must check is V terminal. Now V terminal is external voltage. So in other words, energy that goes into the external part of the circuit. Alright, so let's see our first variable. And these ones, when you get multiple choice questions, don't look at them and see, this one might be right. Go and calculate the answer and then go pick your answer from the options below. So we're going to, the question is, how would this decrease affect the readings on the voltmeter and the ammeter? So we must go and see what happens to V terminal and what happens to I. Alright, so you all know that when we have a closed circuit, this voltmeter over the battery measures external voltage. In other words, V terminal. Alright, so the first variable is R. When R, they told us that R is being decreased. So we are going to write R goes down. And please, when you do the examination, and this is a long question, Don't just make arrows like this, you must write full sentences. So R is being decreased, that was given. They told us that. Now, from Ohm's law, V equals I times R. So from this expression, we can see that when R is being decreased, I increases. They are inversely proportional. That's the word, inversely proportional. So when R is being decreased, I increases from Ohm's law. I'm going to write here Ohm's law. You're going to use Ohm's law to see that. Then, if the total current in the circuit increases, what happens to V lost? I flows through the internal resistor. So they are directly proportional. So whenever I increases, V lost will also increase. Now what will happen to V terminal? Because of V lost being increased, V terminal will decrease. Because these two together, added up, must be the EMF. So if these two added is the EMF, then if this one gets bigger, this one must get smaller. Because they added together, they must be the same constant. So here we see the arrows now. Now the question says the voltmeter V terminal will decrease. The ammeter is the current. Current will increase. So now you go to your options and you look. The voltmeter reading must decrease. Now that one's out. And this one says increase, so that one's out. So it's between B and C. They are both decrease. Then you go and see ammeter reading must increase. And there's the increase, decrease and increase. Answer will be B. Whenever you do multiple choice and you don't feel confident about multiple choice, how do we study multiple choice? We go and do every example that exists. Yeah, so you're going to search on the internet for past papers from 2008. You'll get them with memos on the internet. And you work through every multiple choice question that exists. Because they're not going to think about new ones. They're going to use the old ones. Then we have a longer question. I've picked this one because it's very straightforward. But if you don't understand the all the terms and how everything goes together in a circuit, then you won't be able to do this one, even though it is very straightforward and very simple, because it's most of the information is given. They say to us in this circuit represented below, two 60 ohm resistors connected in parallel are connected in series with a 25 ohm resistor. The battery has an EMF of 12 volts and an internal resistance of 1.5 ohms. Now the first thing you must know is, if we have a closed circuit, if we put a voltmeter over the battery, this voltmeter will measure external voltage. If we have a switch and we open the switch and there's no current flowing, then this voltmeter will measure EMF. So make note of that. That is very important information that each of you must know. I'm going to say it again just because it is so important. If you put a switch in the circuit and the switch is open, there's no current flowing through this circuit, then this voltmeter over the battery will measure EMF. Once we close the switch, then this voltmeter reading will fall to a certain extent. And this means that energy is being taken by the battery, and that's called internal resistance. So V lost will be subtracted from EMF, and this voltmeter will read external voltage. That is very important that you understand that. Okay, now the first thing you must see is that they only gave us EMF. We don't know V lost. We don't know anything else. So we are being forced to work with EMF. So you must please remember, you must match variables. And I want you to write this down. Which variables go together? If you work with the EMF, you must work with the total current and you must work with total resistance. This is very important. Big R is external resistance plus small r is internal resistance. And together these two make up the total resistance in this whole circuit. In other words, you'll have the parallel resistance plus that series resistance plus the 1,5 internal resistance as well. That's what you will work with there. If you want to work with V lost, say for instance we had V lost, then you have to work with total current, because the total current goes through the battery. That is true. And we work with, if you work with V lost, then you must work with internal resistance. So in other words, V lost and internal resistance goes together. They match. You can't use any other variables. These two go together. EMF goes with total resistance. And then the last one I want to show you is V. I'm going to write it external voltage. In other words, all the energy provided to the external current, V parallel plus V in that series, that's V external. If you want to work with that, you work with total current and you work with external resistance. If you know these three facts, or you don't have to go and study this, but this is something that you must know by heart. You must understand this in order to do calculations in a circuit. Okay, let's look at our first question. The equivalent resistance of the parallel combination. Now it's very important that you read carefully, because they ask the equivalent resistance, but only in the parallel part of the circuit. So you're not going to add the series part. Stop when you get to the parallel resistance. Okay, now our rules. If you don't know the rules of series versus parallel, let's quickly write them down. We'll make a table. Okay, and then we have a series circuit and we have a parallel circuit. Okay, I'm going to give you 1 minute to write that down. All right. Now we have three variables according to Ohm's law. Ohm's law says V equals IR. So we have V, we have I, and we have R. And on this side we also have V, I, and R. Alright, so the rule for series, and this you're going to study. The rule for series says V total equals V1 plus V2 plus V3. So addition of voltage in a series circuit equals the total voltage of the battery then. The V of parallel, the rule says V total equals V1 equals V2 equals V3. And this is very important that you know that this is per branch. So if you look at the example on top here, this whole branch, I'm going to do this in in red because it's so very important that you know this. If we put a voltmeter over this branch, the whole volt measurement over branch 1 will equal the whole volt measurement over branch 2. If there were 2 resistors, we'll do one in a little bit. If there are 2 resistors, then you're going to add the 2 V's, so it's for the whole branch. This rule counts. Okay, when we get to this to the current, I total, in other words, the current series, I am going to say that I total equals I1 equals I2 equals I3, because in a series circuit, it's never branched. It never divides. The current never divides. So everywhere in a series circuit, you can say that the current is the same anywhere, even through the battery. You will take the total current. Current for parallel, I total equals I1 plus I2 plus I3. Also, per branch, you add all the branches to get the total current in a parallel circuit. Okay, now for R in a series circuit, we'll do R total equals R1 plus R2 plus R3. And then for parallel, you're going to put 1 over R total, or this can become then R parallel. Let's rather make it R parallel, will be 1 over R1 plus 1 over R2 plus 1 over R3. Very important, per branch. So if one branch has two resistors in it, you'll add them together before you do the 1 over. We'll see when we do this one. So there are your 6 rules that you're going to study from the top of your head, and then we're going to use Ohm's law, V equals IR, and then you can solve any problem, any circuit problem you can solve then. Alright, so let's jump into this one. The first one says the equivalent resistance of parallel. So we're only going to work with the parallel part of this circuit for now, for number 1.1. So our rule says for a parallel circuit, we are going to do total resistance for parallel. So we write down our rule, 1 over R parallel equals 1 over R1, first branch, the whole branch is resistance, over R2, the whole branch is resistance. Alright, so let's go and substitute. 1 over R parallel equals 1 over our first branch. What is the resistance in our first branch? The whole branch has only one resistor, and it is 60 ohms. So we'll put in 60 ohms. Our second branch, here this one, has only one resistor also, and we put in that one, R2 equals 1 over 60. So if you take a good look at that, so 1 over 60 plus 1 over 60. Now, please use your calculator to do this. Don't think you can do it off the top of your head. Rather be safe and use a calculator. So if we add this up, we get 1 over R parallel equals 2 over 60. And then we have to reciprocate it to get R parallel, because we don't want 1 over. We want R parallel, 60 over 2, and that is 30 ohms, and you get all your marks. Please, very important, students forget often, put the unit. Resistance is measured in ohms. Alright, so that is how we calculate number 1, equivalent resistance of the parallel combination. Now the second question says, calculate the total current in the circuit. Total current in the circuit. And as I mentioned before, when we want to calculate the current now, we need to match and see what's given and what is being asked. So if you look at these 3 statements that I put here, all 3 will give you the total current. But do we have enough information to use any one of these 3? Let's see what we have. They're asking for total current. So, let's start at the bottom. Do we have the external voltage? No, we don't. They didn't give it to us. If you look at the sketch, they only gave us 12 volts. So they only gave us the EMF. So you are being forced to work with EMF because you don't even have the V lost. You don't have V external. You don't have V lost, but you do have the EMF. We do have the EMF. And do you have the total external resistance? Not yet, but we can calculate it. Do you have internal resistance? Yes, we do. They gave it to us, 1.5 ohms. So let's go and substitute. We say EMF is equal to I external resistance plus internal resistance. EMF has been given. They gave it to us there on top. EMF equals 12 volts. So we'll substitute 12 into EMF equals, I is the one that they want to know. They asked us to calculate the current in the circuit. External resistance. Do we have the external resistance? Let's see. We have the part that's parallel. We just calculated it down here. There we calculated external resistance. Do we have, okay, so we can put that one in. That's for the parallel part. But is that the total external resistance? No, because we have a parallel part, but we also have this part that's in series with this part. So we're going to add these two together, because what is our rule for resistance in series? Add them together, addition. So we're going to take the 30 from the parallel plus the 25 from the series, and that is 55. Plus, do we have internal resistance? Yes, we do. They gave it to us, 1.5, so we substitute into small r 1.5. And then you go and do the math, and you get I equals 0.21 amps. And that's the second question, and you'll get full marks for that one. Alright, number 1.3. Potential difference across the parallel resistors. Now there are a few options to do this one. The easiest option for me is not necessarily the one on the memo of this question paper. I'm going to show you 2 methods. You go with whichever one you feel most comfortable with. So they want to know if we put a voltmeter over the parallel part, what will the measurement be? Now, if you agree with me, our rule for voltmeters in parallel says V total equals V1 equals V2 equals V3. In other words, it doesn't matter if we put the voltmeter over the whole parallel part or only over this branch. or only over that branch? It makes no difference, because our rule says this voltmeter will measure exactly what that one measures, will measure exactly what that one measures. So it doesn't really matter which part you go and calculate, as long as you do it correctly. So what I would have done is, we have the total current running through this circuit. We just calculated it. It's 0.21 amps. So because the resistors have equal resistance, that means when the current comes to this point, it will split exactly in half. So does that mean we can divide the total current by 2? Absolutely. So we can take I total divided by 2 equals 0.21 divided by 2, and that gives us 0.105 amps per branch. So 0.105 through that one, and 0.105 through this one. And now you can just use them per branch. So if we take, let's name this one R1. V equals IR. So the volt over resistor 1 is equal to 0.105, which is the current in the first branch, times what is the resistance in that branch? Only 60 ohms. And if you substitute that, you will see that you end up with 6.3 volts. Okay, that's option 1. Let's look at option 2. You might find this one a little bit easier. The second one is also V equals IR. But now we must be very careful with what we match together. We want V parallel. If you want the V over the whole parallel part, then you must work with the total current, because the total current flows from there up to the end. So if you're going to work with V total or V parallel over the whole parallel part, then you must work with the total current, and the resistance we're going to use is parallel, resistance parallel. Okay, so we have V parallel equals total I times R parallel. And now you must just go and substitute the right values. So they're asking for V parallel. We have the current, the total current is 0.21. We calculated in the previous one. And we calculated R parallel, which is 30. And if you multiply those two, you get, surprise, surprise, 6.3 volts. Same answer, two different methods. But as long as you get one of the two right, then you're safe. Okay. Now let's look at the next question that I brought for you guys. The next one that I brought is a very short question, but a very interesting one. Learners investigated the conductibility or the conducting ability of two metal wires, P and Q. So if you can see, this is the graph for Q and there is P, made of different materials. They connect one wire at a time in a circuit as shown below. So if you can just take a second and carefully look at this diagram here that they show of the wire. They have a voltmeter over the wire. They have an ammeter in the circuit, and they have a battery. Now they want to know, how do these two compare if you looked at their conducting ability? So quickly study the graph, study the diagram, see what you see. Alright, so they drew a graph of current over potential difference. So this is V, that one is I. I over V. So the first question is, name two variables that the learners would have controlled in each of the experiments. Certain things that must have been taken as a constant. They must have stayed the same throughout the whole experiment. And for this one, temperature of the wires, as well as the thickness of the wires, because when the wires get thicker, the resistance becomes smaller. Then the length of the wires will also make a difference. The longer the wires, the more the resistance will become. So if you want to take a note of that, if you didn't know that, you must please write that down, take a note of that. Thicker, more resistance. If you use thicker wires, the resistance will decrease. Excuse me. The thicker the wires, less resistance. You can think of it as a hose pipe with flow. The thicker the hose pipe, the less the flow will be. The longer the wires, the more the resistance will become. And then temperature. Higher temperature, more resistance. This is important that you know this. So thicker material, less resistance. Longer material, more resistance. Higher the temperature, more resistance. Now they ask of you, the potential difference across each wire is increased in equal amounts, and the resulting current through these wires are measured. Using the measurements, the learners obtained the following sketch graphs for each of the wires. So the first question we answered already. What must have stayed the same? Temperature, cross-sectional area, in other words thickness, and then the length of the wires. Now in the second question, they ask of us, which one, P or Q, is the better conductor? Explain your answer. Now first we must decide, when is something a better conductor than something else? When the resistance is lower. So we want one of these two with a lower resistance. Which one of these two wires, Q or P, has a lower resistance than the other? So let's go and see. And the answer is again in Ohm's law. V equals IR. So we have the same battery over both. So V, let's go and look at potential difference. Let's take this potential difference for instance. If you go up in the graph, we'll see that for the same potential difference, P has a lower current. See, for this potential difference where the current is for wire Q. Wire Q has a much higher current than P for the same value of V. So when I goes up, R goes down. So we want the wire with the most current, and that would be wire Q. So Q would be the better conductor because it has a higher current running through it, therefore has a lower resistance. So you will write the answer in the form. Remember, the first that they asked was, which one is the better conductor? So your answer will look like this. Wire Q. That's your answer. They asked which one is the better conductor. So you will say wire Q. And now you will explain your answer. So now you will say for the same, please write full sentences. Don't do this in little arrows and little pictures and stuff. Write full sentences. So you are going to say, for the same potential difference, wire Q has a higher current. Therefore, wire Q has a lower resistance than P. And you'll get full marks. So if you want to write that down, you're going to do this part in pencil in your exam. But when it comes to writing your answer, this is what they're looking for, this one. In words, not little pictures and indications and arrows. Quickly write that down. All right, let's look at the next question. The next question that I brought for you is a little bit more challenging. And just because we have two branches in the parallel part, but the one branch, this bottom branch here, consists of two resistors that they put in series to each other, but in parallel to that one. And if you see then, there's another resistor up here, 2 ohm resistor, and that's also in series with this whole parallel part. So this one has a lot of resistors, which makes it a little bit more challenging, but not if you understand all the fundamentals that we talked about earlier. They also give us the internal resistance, 0.8 ohms, and they give us 12 volts for the EMF. They say in the description it has an EMF of 12 volts. All right, let's look at the first question. Our first question says, calculate the effective resistance of the circuit. Now the first thing you must see is they don't say stop at the parallel part. They say the total effective resistance of the circuit. And another thing that you must please write down is effective resistance. The total effective resistance includes internal resistance. It's very important to know that the total effective resistance of this circuit will include the internal resistance. So if we go and calculate this, firstly we must calculate the parallel part. So let's quickly do that. Our rule again, let me find my rules. What is the rule for resistance in parallel? 1 over R parallel equals 1 over R1 plus 1 over R2 per branch. Per branch. So, let's see if we can fit everything into the screen. No, we can't. We write our rule down. 1 over R parallel equals 1 over R. How many branches do we have? 1 branch, 2 branches. This is 1 branch. So we have 1, 2 branches. So we're going to write 1 over R1 plus 1 over R2. Because we only have 2 branches in the parallel part. Alright, so 1 over R parallel equals, let's substitute. What is the first branch's resistance? 4 ohms. So we're going to substitute that one directly like that. 1 over 4 plus. Now watch out for this. Our second branch. Our second branch has 2 resistors and they are in series. And what does our series rule say? Our series rule for resistors says R total equals R1 plus R2. So then we go and add them. 8 ohms plus 8 ohms is 16 ohms. So our second branch has a resistance of 16 ohms that we substitute. Now once again, 1 over R parallel equals, please use your calculator for this. So we have 1 over 4 plus 1 over 16. Okay, you don't have to do all these steps. I just want to show you everything comes from. It's not necessary to do all these, but please for this part, use your calculator. And then you say 1 divided by answer and you get R parallel is equal to 3,2 ohms. Once again, we need units. Okay, but we're not done yet. We don't have effective resistance of the whole circuit. We only have the parallel part now. So if we want to do effective resistance, R total is equal to R parallel plus, and remember this one is now in this one is in series with this whole parallel part. So we put R parallel plus the R series resistor. And when we substitute, we see that parallel, you already calculated that, 3,2 plus the series resistor is this one, 2 ohms. So we add the 2 together, 2, and this is equal to 5,2 ohms. Okay, but this is this now total effective resistance? No, not yet. Why not? Because we said that effective resistance includes internal resistance, and we haven't added that yet. So we have the external resistance of this part, this whole part here. External resistance is equal to this 5.2. So if we add the internal resistance, then we say R effective, oops, that's with a C, is equal to R plus R, and that equals 5.2 plus 0,8, and that is 6 ohms. And you will receive all your marks. I'm going to move this up a little bit so you can make sure you have all this written down. Alright, so you should have all that down now. I am going to give you 5 minutes to do number 9.2. I'm going to give you 5 minutes. It should be more than enough. If you want to work in groups, you're more than welcome. Don't confuse each other, but let's try this one on our own. The question is, what is the reading on the ammeter? Now, there it is. There is the ammeter. So, we are trying to calculate I total. I'm going to give you 5 minutes. I'm going to leave this just like that. Calculate I total.